Hello. In this talk, I will walk you through the components and the architecture of my submission to this year's shared task, which is about the prediction of cognate reflexes. So just as a quick reminder, we have a training set and the test set. The training set consists of a collection of cognate classes from a group of related languages. This is illustrated here in the first table, all in IPA transcription, and the test set is just one row of such a table, meaning we have cognate reflexes of the same cognate class for several languages, but for one of the languages, the reflex is masked, and the task is to predict which word should go in here. For this example, for the cognates of Latin pisci, this would be French psh, for instance. The system I'm describing implements 3 steps to achieve this task. In the first step, multiple sequence alignment is performed, both for the training data and for the test data, which means arranging all the reflexes of a cognate class in such a way that cognate sounds are arranged in one column, such as, for instance, the P and F in the initial position for this particular example. And then this reduces the prediction task to a prediction task, imputation task for each column separately. So the system I'm describing doesn't use syntagmatic information, but data imputation is done column-wise in a multiple sequence alignment chart. If a word doesn't have a reflex of a certain cognate sound class, then the system inserts a gap symbol. Second component is phylogenetic information. So the system uses the degree of relatedness represented by a family tree for data imputation, and this tree or distribution over trees is inferred from the training data. For the running example, the collection of trees inferred looks like this. So it doesn't have a very good resolution due to data sparseness, but it's still helpful to figure out the correct sound for each alignment column. And the final step is then to actually carry out this data imputation for each column based on the phylogenetic information. So gap symbols are treated as regular symbols in the phylogenetic and data imputation stage, and the final step is then to delete all the gap symbols for the alignment row in question. Let me go a bit deeper into the various steps. So multiple sequence alignment is a complex problem. The system starts with a simpler problem, namely pairwise sequence alignment. This is implemented using a pair hidden Markov model. So this is a hidden Markov model with 2 output tapes. The particular architecture used here looks like this. So we have 4 states. The match state emits a symbol on both tapes. X only emits on the first tape, Y only on the second tape, and doesn't emit any symbol. The parameters, so the transition probabilities, are trained using all cognate pairs from the training data using the EM algorithm, and then to actually predict a pairwise sequence alignment for a pair of cognate strings, the Viterbi algorithm is being used based on the trained pair hidden Markov model. And then this can be lifted via a heuristic approach to multiple sequence alignment. For this, the system uses progressive sequence alignment. Assuming a guide tree, progressive sequence alignment carries out pairwise alignment between alignment blocks recursively bottom up through the tree. This approach is known to often return suboptimal results, so the system in its final form uses a variant thereof, which goes by the name of T-coffee alignment. So this is an algorithm which comes from computational biology. In the first step, the alignment parameters, so the weights for each pair of sounds, are re-estimated by first doing all possible pairwise alignments and then combining them to indirect alignments. This gives us alignment weights between sound occurrences, so tokens instead of types, and then these re-estimated weights are used for a progressive alignment. Okay, this is applied to the training data. All the alignment blocks are concatenated. And the next step is phylogenetic inference. The assumption is that each column results from a Markov process, which runs on a phylogeny. So the proto word has a certain sound, and then there is a Markov process which leads to random mutations. If a language branches, then we have independent copies of this mutation process running along the branches. So mutations are modeled using a Markov process for which we need a mutation rate parameter. Then we have a phylogeny, and the mutation process runs on all the branches. So if a language splits, then the state of the mother language is copied, but the mutation process runs independently on the daughter branches. We only observe the states at the leaves of the tree, and we don't know the mutation rate of this Markov process, but via Bayesian inference, given suitable priors, we can take the observed states at the leaves as given and then infer posterior distributions for the missing parameters, the phylogeny and the mutation rates. As already shown on a previous slide, for the running example, the posterior distribution of phylogenies looks like this. So we have a strong signal, for instance, that German and English are closely related, but the position of Albanian and French are very uncertain, and also the amount of mutations, which is reflected in the depth of the tree, is very uncertain here. Using the posterior distribution over phylogenies and over mutation rates, the system predicts a posterior distribution for missing entries. So here the example on the slide takes a typological example, but it's the same to impute missing entries for alignment columns. So if we know the states for a group of related languages and we have an estimate of the phylogeny, then we can compute the likelihood for all possible states for this particular language here, and via normalization this gives us a posterior distribution, and the maximum a posteriori state is chosen as the state imputation for this particular language. Applied to our running example, the predictions are, for instance, a P for the first column here. So you see that the phylogenetic information supplies the information that Albanian and Latin are more relevant for predicting the French reflex here than English and German. Because English and German are so closely related, they are basically counted as one here. The system predicts then an E for the second column, so the phonetic reduction which took place in French is not adequately modeled. The sh is correctly predicted, and the K again was victim of phonetic reduction in French, which is not modeled here. And finally, we have a gap symbol in the final column. The final prediction then results from removing the gaps after doing these imputations. So for this particular example, as indicated already, the prediction would be Pishk for French. Okay, let me close with a comparison of this system to the other submissions to the shared task along the various dimensions used for evaluation. The system is somewhere in the middle of the pack. But what is perhaps noteworthy is that the system is not very sensitive to the amount of training data.